Okay, fine. So thank you, everybody. And wow, I remember when everybody first in like a normal classroom. Anyway, so I'm Peter Lofberg. I just want to talk a little bit about what's going on in our industry and some of my observations and what I think can be done or not done, and I think I don't really know. We are trying to make a network work, and if you go and talk to users, the thing they start asking for is at some point they say, I want it to work now and I want it cheap, and I want it reliable. And then we are trying to address this in all sorts of ways, and right now there is a whole industry of people trying to make boxes that do things that I really don't understand what they're good for. You can actually make everything that I can hear people asking for in the space of where we are operating using just IP packets. I just don't see why we have to go around with all sorts of things all the time in trying to just fix the problem. We ended up in a very funny scenario right now where people are trying to do all sorts of buzzwords again. For a while we didn't have that money to deal with, but now we're back. And some other people are actually trying to outmarket each other, and we're getting to the point where I saw like Tragwag, we're comparing SLAs of service providers, and the top one, they were much faster than speed of light, so they solved a lot of problems. So if you look at the last line there, it says OSI, ATM, and you can figure out what word I didn't put there instead of etc. They all look fantastic until you try to actually make it work. For once, I thought we got rid of these people that were trying to put things underneath our IP network and make it really hard to operate. Unfortunately, they were replaced by new people, and maybe. If you were to build a network, you could build a network that looks like that. The thing in the middle, which I call IPv4 transport, is something that just moves IP packets. IP packets could be IPv4 packets or maybe even IPv6 packets. But for now, IPv4 packets. And then you end up with all those things that people want to sell. They call them services. They call them all sorts of things. And there's nothing that I can't figure out that you just can put on top of the transport core. The feature of doing it this way is that you can keep your network then very simple. And the middle of the network actually can do at the same time serve the function of being the public internet, which is the thing that actually makes things go round. There are all sorts of quality of service stuff, and there are all sorts of things here. And let's go look at how you can do some of those with just using IP in the middle of the network and not try to make it so complicated. For the ones who doesn't understand what Denver Duck service is, there's a company that actually is now the local company, the Arbach here. I asked them at one point why they were talking big about IP or optics, and I asked them why they were building an ATM service, and they said, well, we have to feed the ducks in Denver. The core of the network, its job is pretty simple. The job of the core of the network is to move packets. Okay? If you try to make the core of the network understand what every customer is asking for, what every customer's need is, and trying to figure out what to do with all those things, you tend having a fairly complicated network configuration, or you have some protocols that actually build states in the network. And maybe you can build that for one customer at a time, and you layer them on top of each other. So every time you get a new customer special requirement, you configure it, you verify that it works, and it's all fine and dandy. But what happens over time is that your network gets bigger, and you get new boxes, and you get faster boxes, and your topology changes, and something breaks, and rerouting happens. And it means that if the network actually performs a lot of functions that are what the paying customers are paying for, you have to retest every time something changes to make sure it actually does the right thing. This MPLS people with tunnels, you get an n squared problem of figuring out how routing works, even if that you actually get more circuits than you physically have, right? So you get more headache than you would have if you hadn't done anything. There's a lot of work that has to be done on the routing protocols we have today, like BGP and our IGPs are not optimal for what they're trying to do right now. And there are things that could be done to them, or maybe some of them we just need something new. But most resources and all the vendors go to the department of bus, which is the people that don't do all sorts of things, that doesn't really move packets. I think that the functions that the people need, you can all do at the edge. And I said value add and value remove. Okay? If you end up building a perfect network and somebody wants to pay less, you have to produce a worse service than you had from the beginning. So that means you have to throw their packets away and delay them and do stuff. There is some history behind why we're going the way we were going. In the old days, bandwidth cost a lot of money, and if you were working internationally, if you went into a country, the cost of a circuit was basically a 24/7 phone call with 20% off. So you had to find ways of using that circuit, basically oversell it in order to make any money at all. But today, when you can buy fiber so cheap that it's not even funny, bandwidth is not an issue really. So a lot of stuff was built around assumptions that are no longer valid. I talked to a friend that works for a service provider, and he said, well, they're replacing our boxes and installing new boxes because they have to have boxes that are capable of quality of service in the core. And I don't know. So network quality of service. This is the quality of service of the thing in the middle of my picture. The only thing it needs to do is reliably deliver packets, right? And if something goes wrong in the network, if fiber breaks, some router breaks, some software crashes, you have to restore services, find another alternative route, or get the thing that was breaking back in service again. And some people say, oh yeah, you have to have an underlying optical network that can do perfect wires. That's fine, but a perfect wires doesn't end up in perfect routers. So the problem doesn't really go away. Something that we are pretty bad at is knowing what the network is doing. While the network is moving packets and everything is fine today, you have to be able to figure out what is the network doing, who is talking to whom, where's packets coming from, where are they going, who is talking to whom and why, and try to guess what's going to happen in the future. Depending on where you're trying to do things, you have to do either traffic engineering or capacity planning. And capacity planning means that you have to write small papers or send out digging machines, and you really want to understand what's going on, because if the circuit is overloaded, maybe it's not the endpoints of that circuit that actually generates the traffic. It may be smarter to put the circuit in between two completely different points in the network to offload it. And most of the restoration schemes you end up seeing on networks of any size today are spaghetti. You don't want the network to reorder too many packets, and you want the core to be able to carry a large packet. I put 4470 here. The game here is that you want the core of the network to move bigger packets than Ethernet, because Ethernet is the de facto standard that you demark to a user with. I mean, Ethernet is it, period. The 4470 came from historical reason. I think it's basically started off with SDDI being able to do that, and then all the wide area high-speed network interfaces actually did that, or something bigger. There are recent Ethernet standards, and some of the ATM people can do 9K or something. So the trick here is you have to be able to carry a bigger packet than if you're giving the user. So if you're giving the user 1500 bytes over an Ethernet, you really want to be able to wrap that into something to do the stuff that people think they need. So if you look at a typical core, and this is not any particular network providers, this is numbers where I try to figure out what numbers make sense before the cost of running and operating and building the network goes through the roof. And basically, if you're trying to build the core of the network that is better than this, the cost goes up, or the operational impact is so heavy. I mean, you can't basically capture or restart a router in a year without getting outside the 5 nines of availability. But if this is the criteria that you have to have 5 nines of availability on, you can actually do a pretty decent job using IP technology and a connectionless network. I don't think there's anything strange in there. So my point is that if you have something that requires a better network connectivity, a better performance, or a TDM kind of type service, or TDM-like service, you're better off buying a TDM network, because I can't do it very well with IP networks or packet networks. Then people say, okay, you need call to service in the backbone. This graph shows the queuing delay of a router. And the vertical scale is milliseconds of delay. Okay? The horizontal scale is load of the circuit, and the green one is a T1. So you see that on a T1, when you start to load the circuit at 60, 70, 80%, you're actually introducing queuing delay, and it goes through the roof. So if you have packets that are real-time packets. You may win by putting them before the packets are not real-time packets because there is an outbound queue. Look at the P3 circuit. The queue starts to build up at like 60% load. Okay, so that makes sense. The red line is a 10 millisecond. That's the time it takes to send an optical signal from New York to Chicago. Okay, one way in optics. That's the speed of light in glass. It doesn't get faster. So, people get confused about the switching delay in routers versus queuing delay in routers, and they forgot that they are order of magnitudes much smaller than the queuing, than the propagation, than the speed of these bits in glass. Now, if you increase the backbone circuit, I still kept the T1 there, and you put an OC-free backbone circuit. Okay, your queuing delay starts to the quality of service by prioritizing packets starts to kick in at about 80% load. And if you go to an OC12 network, you actually have to get a 90% load of the circuit before it makes any sense. Does it do anything to you? At an OC48 network, you have to get over 97% load on your backbone before your queuing makes absolutely no sense. Or before your queuing makes any sense, you have to load your circuit at 98%, which is tricky. So you're only playing with very small margin. Today, everybody has an OC192 network, and with an OC192 network, you have to load the network up to 99% before your queuing delay becomes an issue, and the gain of doing priority queuing in your backbone is basically zero. Okay? If your circuit is overloaded, yes, you're in trouble, but there's no reason for overloading a network today. You can make it work with the cheap facilities available in any way. Okay. So the backbone quality of service is not really needed as long as it's working. Then you get to what the customer wants, and the customer, they have all sorts of weird ideas of what they want. And if you can do that at the edge, it's fine if you can find a way of figuring out how to turn it into product. Maybe we can learn something from the cell phone people. Anybody? I don't know anybody that can figure out what their cell phone bill is going to be next month. It's so complicated that you don't know what's going on, and people still have to pay anyway. So customer quality of service is something you can do at the edge, right? Because the core is out of the picture here. So if you're on an oversubscribed link, or if your bottleneck is a circuit to the customer, maybe the T1 circuit, and he wants to do voice over IP, and he also wants to do FTP transfers, there's a win of putting the voice packets before the FTP transfer packets. Now, it doesn't matter what kind of transport you're using. If it's ATM or MPLS or IP, you have a queuing problem, and you have to figure out how to do queuing or queuing strategy. But then you can look at the packets, right? And it becomes a problem of, I have 5 different queues. I now have to look at my traffic and say which packet goes into what queue, and there's a couple of ways of doing it, but there's nothing like wrapping is the bottom line, right? Which is where, for example, MPLS falls in. It's just that, you look at this label, and that label goes in a certain queue, and it gives the user the availability to tag its packets, but you can have done that through other means too. Then we got the quality of service thing. I'm too tired. The quality of service thing taken care of, okay? What do we need to build services to users? Well, they ask for 2 things basically. They ask for point-to-point circuits, and they ask for point-to-multipoint clouds, and they sometimes think they need a point-to-multipoint cloud where the cloud actually understands their IP routing and have multiple route views. The 2 products we end up having is the public internet connection and the VPN service. Now, there is nothing that you can do this with IP headers, right? So what you do is instead of using UTI is basically MPLS but using IP headers. I just put a funny word there. So basically what you do is you take a layer 2 packet. It could be a packet over SONET frame, an APM frame, and I put AL5 only there because you really don't want to take people's voice traffic or their circuit emulation traffic and try to put it on a packet network, because if you remember my SLA for the core, they don't need 3-second playout buffers, and nobody wants a circuit for voice with 6-second round-trip delay. You can do frame relay trunk or multi-point. You can do IP and IP, which is called GRE. You can do MPLS labels in UTI, or you can just stick Ethernet frames. If you're demarked to customers Ethernet, you can actually do Ethernet frames straight onto an IP packet. And if you really want to have multiple circuits on that same Ethernet, you do the 1Q VLAN encapsulation. The feature is that everything you look at that the people are trying to sell right now, there are variations of encapsulation, and the method of encapsulation doesn't really matter as long as you can carry it. Let me just skip those slides. Yeah, but it's too long. I'm going to show this slide because it's simpler. Let's say that you are having an Ethernet that demarks to a customer. What you could do is that you say, okay, the edge box, we just take Ethernet frames and put them in a tunnel, send it to another router that where the logical interfaces reside. So that way you can even do service provider selection and you don't need to do PPP or E or something. The point being that we can use IP as transport for any layer 2 service. So it's going to be layer 2 over layer 3 over layer 2 instead of. So if you look at an end of this, you have the incoming Ethernet right from the side, from the left side, and that's facing the user, the customer. You can just take different VLANs and map them into different endpoints. So you basically map one endpoint, one VLAN into an IP source destination pair, and that's the encapsulation. And you can do exactly the same thing that you can do with any other encapsulation, frame relay, MPLS, APM, whatsoever. It's just that it rides on top of an IP network, and it doesn't require anything more than of the underlying transport that it can just forward the packet safe and reliable. A lot of people are talking about VPNs. So bottom line is, if you want security, it's called IPsec, and it runs at the host, because anything else is just not really secure. I mean, you have somebody plugs a wireless station into your internal house network, which is inside firewalls, and you can stand outside on a car, or somebody else walks in the door following somebody and they plug in, or some of the internal people are doing something wrong, or somebody managed to send a virus or a program to somebody that actually was a sniffer that exports things to the outside world through their normal mail system. All of those problems are solved if you're actually encrypting things end to end. But as long as there are people that believe that wires are secure, you could build a VPN network using the public internet, and you can find ways of, instead of trying to have the network do all the work, you can actually have the edge of the network to do all the work of doing a VPN. Assume that we had a box that looks like this. The IP transmit core is the thing. You can replace that with public internet, right? It has a circuit that goes to this box, and this box has 2 routers instead of 1 inside. So the first router, which is connected to the thing called outside, that is like a normal internet connection. Then you have an encryptor, and the encryptor is that multi-channel, so you can actually encrypt packets, and you put a VC or whatever you want to call it in front of the packet, so you can have multiple channels. And then there is a router on the inside. The router on the inside will only see virtual interface. We will see point-to-point links or point-to-multi-point links to other boxes. And the router on the inside doesn't know that it's running over a tunnel at all. And it's encrypted, so we got real security. So if you're on the outside, you will only see packets coming from the inside are always encrypted. The router on the inside then just can run any routing protocols on its tunnels. And now you're saying, okay, you created tunnels. How do you configure them? Well, it's an edge function, right? Some people know how multicast PIM sparse mode works. In PIM sparse mode, you have a rendezvous point. So what you do is you configure the last hop routers to say where the RP is. And somebody wants to join a multicast group that, because it sees IGMP join messages on the local network, it will send the join towards the RP, and that will trigger building forwarding states from the RP towards that user. If the source starts to send traffic, it will send packets, register packets initially to the RP that decapsulates them and dump them on the shared tree from the RP. So the meeting point is there, and then there's machinery around it to make sure that we build a tree from the real source to all its receivers later on once we have to find each other. You can do similar machinery here. Instead of trying to put all of this in BGP, okay, as a disclaimer here, you can put all of this in BGP. You can actually build routers that sits inside the network that participates in every VPN. So they have like a forwarding table for every VPN that gets populated by the different NLRIs in BGP. Right? So if you want to go down that path, it doesn't matter what kind of encapsulation you're using. So it can be IP and IP. But the same machinery they're using to build all those tunnels and the same machinery they were using to build all those multi-protocol. I wonder what I had in the pockets. All the machinery they're using that today has been designed to do MPLS doesn't really care if it's MPLS headers or IP headers. You can just use the same machinery. But I'd really like to push this at the edge, and if you want to put it at the edge, the missing piece here is a discovery protocol that will find out, okay, I'm VPN blockbusters. Where are the members of VPN blockbusters? Well, you can configure the RP, right? And then the smart crypto people we can have can help us say, okay, here's how you sign those messages and make sure we don't get denial of service attacks. And now, poof, you can go find all the members of this VPN, and then the outer router, together with the protocols, can actually go and build all the virtual circuits that go in between them on the outside of the network. The feature of this is that anybody can do it, and it will actually run across the existing internet from across multiple providers. So I made another slide that looks slightly different that shows the same thing. It solves a problem that we are having with managed router networks or VPNs today, is that the NOC has to be inside all those thousands of VPNs in order to monitor the networks, and it's actually a security problem. If you build something like this, the provider management, I've forgotten R, the provider can be sitting on the outside because the DM said is on the inside of the network. So if you're sitting on the outside router, you can monitor the performance of the network for every box that is part of it and make sure the wide area service works fine, being on the outside, not having to be on the inside at all. So what would happen is that you have an RP in the top, everybody reports to the RP, and then you will build the tables automatically. And I got out of this argument when people say, well, if you're doing circuits over the internet, or if you're doing circuits over anything, you have to configure it. You can actually make it out to configuring. I just wanted to say and point out the bits and pieces of that, and maybe we can use IP to do a lot of things that we're currently trying to do with other kind of technologies, and maybe those other kind of technologies, once we finally get them deployed and get them working, are not really doing what they were supposed to do because it's so complicated, or the products weren't not already there, or the development effort and testing effort is just too big to get it there in time to make it work. Well, that's about it, Susan.